I'd like to note here that linear page table with like with a million entries is not really what real life is. Actually, tables are not non-linear, so it's not like, I mean, it's much simpler than having 1 million entries in the page table. Okay, but we're just going to assume for now that you have a linear page table. So what does a page table entry have? The linear page table consists of page table entries. Each, basically, you'll have a page, basically a translation. So you have 20 bits for translation, for example, 12, 15, whatever. But you have also some other bits that basically tells you some information about the pages in this page table. For example, you have something that's called some protection bits that basically says that this memory frame, this page frame, okay, is readable, is can be written to, or can be executed from. So basically, if it's for example something that you would execute, then this is a page frame that will have code. If it's something that you read from, then it's a read-only page frame. If it's something that you write to, then it's basically a write-only page frame. If it's read and write, then it's a read and write page frames. And this also enables you, since as we said, you can have these, you will have a page table per process. That means that you can also share some pages between different processes, having the same page, okay, the same physical page shared between multiple processes, but for some of them it's read only, for some of them it's read write, and so on. You have something that's called the present bit. We are going to talk about swapping later, but you might have faced the case where your computer basically use the entirety of the memory of your computer, and when you do that, you typically offload some of the pages or some of the data from your memory to run on disk, to be stored on disk. And when you need something from this memory location, you read it from disk, sort of extending your real memory to actually also encompass parts of your disk. So the present bit in the page table basically indicates if this page has been swapped, is now on disk, or if it's still in memory. The dirty bit is it's basically a bit that indicates whether the page has been modified since it was brought into memory. So that in many cases, when you're reading from memory, you want to make sure that it's consistent. You want to make sure that for example, that the cache is consistent. So you basically check when you're trying to access something from the cache, for example, you check if that data in the cache has been changed in the main memory or not, using the dirty bit. If you try to access something from the cache, you go quickly check if the dirty bit is raised for this page in the memory. If not, then you can just access it from the cache. If yes, then you'll have to go and fetch the new data from the memory. And then a reference bit, which is basically used to track whether a page has been accessed ever or not. And this is basically useful because sometimes if you're swapping, or if you want to move some things out of memory, if you want to clear your memory, then you check the reference bit, and the popular pages stay in memory, the other pages move. So this would be a typical entry in your x86 page table, where you have 20 bits for the address translation. You have a few other bits, basically flags that tell you, is it readable, like read write, is it executable, and so on. So we need to also note that, of course, if you're searching 1 million entries, paging is too slow. Okay, so the move 21 to EEX line is no longer just is no longer going through 8 pages. It's actually now you have 20 bits to translate. So you extract the VPN from the virtual address. This is the first thing that you do. Okay, if you have 20 bits, that's a sad thing. And then you form the address of the page table entry by basically getting the VPN multiplied by the size of the page table entry, plus the PTBR, which basically is sort of your translation. You then fetch the page table entry, and then you check if the process can access the page, and if it can access, then you can get it. Otherwise, you do a segmentation, you raise a segmentation fault, and then access okay. You actually fetch the real data, which is really long process. So next time we're going to talk about paging smaller tables and how do we improve in general the paging system that we have described now.